Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through the quiet strangeness of worlds beyond our solar system. For now, imagine standing at a dark window and looking toward a sky that seems familiar at first. Stars scattered like soft points of light, each one calm and distant. Around many of those stars, hidden from ordinary sight, are planets stranger than anything our ancestors could have placed in a map of the heavens. Some are so hot that stone may soften and flow. Some are so dark that they wander without a sunrise. Some circle two suns, some cling close to their stars, and some may be wrapped in oceans, clouds, glassy rain, or deep atmospheres that turn the idea of a planet into something wider and more dreamlike. Out there, worlds exist that defy almost everything we once believed about how planets should behave. There are blazing giants so close to their stars that their skies glow with vaporized metal. There are dark, wandering worlds with no sun at all, moving silently through the cold between the stars. And there are places where the very idea of land, sky, and ocean begins to break apart into something far more unfamiliar. A useful doorway into strange planets is the idea that our solar system is not the default pattern. For a long time, astronomers expected other systems to look roughly familiar, with small, rocky worlds close to the star and colder giant planets farther away. The first waves of exoplanet discoveries showed something much richer: giant planets skimming close to their stars, worlds on stretched, elliptical paths, planets orbiting pairs of suns, and compact systems where several worlds fit inside a space smaller than Mercury's orbit. With each new discovery, the universe reveals something unexpected. Something that stretches the imagination just a little further. These distant planets are scattered across a cosmos far more diverse than we ever imagined. There are worlds where iron may fall as rain at night. One of the strangest ideas in astronomy is that rain does not have to be water. On the exoplanet WASP-76b, the day side is so hot that iron can vaporize into the atmosphere. Powerful winds then sweep that iron vapor toward the night side, where temperatures drop enough for it to condense into droplets. In other words, the planet may have weather made from metal. Not everywhere, and not in the calm, silver way the phrase suggests, but in an infernal cycle of heat, wind, and condensation, unlike anything on Earth. The world is locked to its star, which means one side faces daylight all the time, while the other remains in darkness. That permanent contrast helps drive the process. What makes this so gripping is that it sounds like fantasy, yet it emerges from real observations of a real planet. Even the word weather feels too gentle for something this extreme. Some planets are so hot, metals can evaporate into the sky. Far from being rare curiosities, some giant planets live so close to their stars that ordinary ideas about weather begin to fail. On these worlds, the heat is not just fierce. Temperatures can climb high enough to rip apart molecules and turn metals into vapor. So, iron, magnesium, and other heavy elements may drift through the atmosphere like ghostly gases. A rocky mountain could not survive there. It would soften, flow, and eventually become part of the air. These planets are often called ultra-hot Jupiters, though the name hardly prepares you for what they are. They race around their stars in blistering orbits and endure a constant flood of radiation. For astronomers, they are astonishing laboratories. By studying their glowing atmospheres, scientists can watch chemistry unfold under conditions no world in our solar system can match and discover how much stranger a planet can be than anyone once expected. Some strange planets orbit two suns instead of one. For centuries, double sunsets belong to myth and fiction. Some planets truly do circle two stars at once, tracing wide paths around stellar pairs that orbit each other. The first confirmed example to seize the public imagination was Kepler 16b, a world where two suns would hang in the sky together. It is hard to overstate how much this changed the feeling of the universe. A solar system no longer had to look like ours. It could be built around a partnership. Days, seasons, and shadows on such a world would be shaped by two moving sources of light, not one fixed sun. Even the sky would feel less predictable. These planets also proved something important about nature. Planet formation is tougher and more creative than we once thought. In a place where two stars are constantly tugging at surrounding material, worlds can still emerge and hold stable orbits for ages, quietly circling both suns together. Part of the strangeness comes from how we discover these planets. A planet may reveal itself by dimming its star during a transit, or by tugging the star into a tiny wobble, or by being seen indirectly through gravitational microlensing. Each method finds certain kinds of worlds more easily than others, so the map of known exoplanets is not a perfect census. It is a lantern sweeping through the dark, showing us one surprising room at a time. Rogue planets wander through space with no star at all. Most planets belong to something. They orbit a star, keep to a family, and move through space as part of a system. Rogue planets break that picture completely. These are worlds that drift alone through the galaxy, untethered to any sun. Some may have formed around stars and then been flung away by gravitational chaos, cast out during violent encounters with larger planets or passing stars. Others may have formed in isolation from the start, more like failed stars than escaped planets. Either way, they wander through darkness on journeys that can last billions of years. At first glance, such a world seems hopelessly dead. But it may not be that simple. A thick atmosphere and leftover internal heat could keep some rogue planets warmer than expected, especially deep below the surface. That possibility makes them feel even stranger. A planet does not always need a sunrise to remain a world. Sometimes it can carry its own hidden story through the dark. One known world may have a glowing ocean of lava. 55 Cancri E is the sort of planet that makes Earth feel almost impossibly mild. It is a rocky world, not a gas giant. Yet it orbits so close to its star that its surface may be covered in a vast ocean of molten rock. Imagine a horizon made not of water, but of liquid stone glowing orange and red beneath a dark sky. This world is likely tidally locked, so one side receives intense stellar heating again and again, while the rest of the planet struggles to redistribute that energy. Astronomers have even found signs that it may hold an atmosphere rich in gases released from its hot interior. That matters because it suggests the planet is not just a dead cinder. It may still be geologically active with magma, gases, and heat locked in a fierce exchange. This is not simply a hot rock. It may be a living furnace reshaping itself under a sun that never lets up. Some planets travel around their stars in less than one day. A year on Earth feels natural because it matches the rhythm of our seasons and lives. But some planets make a full orbit so fast that an entire year can pass in less than a single Earth day. These worlds cling so tightly to their stars that gravity keeps them in relentless motion, circling again and again at distances that would seem impossible to us. One lap and their year is over. This changes everything about how such a planet exists. The star looms huge in the sky. Tidal forces may lock one hemisphere into constant daylight. The atmosphere, if there is one, must cope with extremes that our solar system barely hints at. What is so captivating here is the collapse of familiar scales. On these worlds, the phrase "next year" loses all meaning. Time itself feels different when a planet races through its orbit faster than Earth spins through one ordinary day. There are planets so dark they reflect almost no starlight. We often imagine planets as bright spheres catching the light of their stars, but TRES-2b shattered that expectation. This gas giant is one of the darkest known planets, reflecting so little light that it is darker than coal. It does not shine back at space in any familiar way. Instead, it seems to swallow starlight almost completely, leaving only a faint red glow from its own heat. That darkness is not just eerie. Something in the planet's atmosphere appears to absorb rather than reflect, even though the world is hot enough to glow. It suggests clouds, chemistry, and light can behave in combinations that feel almost unnatural to us. A planet can be burning and still look black. That contradiction is part of what makes strange planets so addictive to think about. Hot Jupiters are especially important because they changed the old picture so quickly. These are gas giants with masses like Jupiter, but orbits measured in days rather than years. They probably did not form so close to their stars in the simple way Jupiter formed far from the Sun. Many likely migrated inward through their young planetary systems, reminding us that planets do not always stay where they were born. They do not simply offer new places. They force new meanings onto words we thought we understood, like dark, day, and sky. Some worlds may be covered by oceans deeper than Earth can imagine. Earth feels like a water world until you compare it with what may exist elsewhere. Some exoplanets could be wrapped in global oceans hundreds or even thousands of miles deep, with no continents, no shorelines, and no familiar meeting place between land and sea. On such worlds, the descent would not end in a rocky seabed like ours. Pressure would rise to such extremes that water itself could transform into exotic forms of ice, even while temperatures remained high enough for liquid layers above. That means a planet could hold an ocean, then a buried shell of compressed ice, then rock far below. It is a beautiful and unsettling arrangement. These worlds might look calm from space, blue and serene, yet their interiors could be stacked in layers unlike anything on Earth. They widen the meaning of ocean beyond recognition. Sea does not have to mean beaches and tides. Sometimes it means a planet almost entirely claimed by water. One bizarre planet may be stretched into the shape of an egg. A planet named WASP-12b is so close to its star that gravity is pulling it out of shape. Instead of remaining nearly spherical, the planet appears stretched by enormous tidal forces into something more like an egg or a football. That alone is extraordinary, but the story gets stranger. The same gravitational strain is helping strip material from the planet, drawing gas away toward the star and slowly tearing the world apart. So, this is not merely a misshapen planet. It is a planet under visible stress, being distorted and consumed by the very star it orbits. Its year lasts just over a day, which tells you how brutally close it must be. We are used to thinking of planets as stable things, settled into neat forms by gravity. This world shows the opposite. A planet can be deformed, heated, and eroded until it becomes something temporary and tragic, a place caught in the act of losing itself. Strange permits have changed what we thought a planet could be. Not long ago, planets seemed easy to picture. There were rocky worlds, giant worlds, moons, rings, and a neat solar system to measure everything against. Then, exoplanet discoveries arrived and smashed that tidy picture apart. Astronomers found giant planets hugging their stars, worlds circling two suns, planets darker than coal, planets with lava surfaces, and lonely wanderers with no star at all. The result was bigger than a list of oddities. It was a change in mindset. Our solar system stopped looking like the template and started looking like one example among countless possibilities. That shift may be the most astonishing discovery of all. The universe was not merely more crowded than we imagined. It was far less predictable. With more than 6,000 confirmed exoplanets already found and billions expected across the galaxy, the real lesson is humbling. Planetary nature is more inventive than human imagination first allowed. And it may still be only getting started. Some giant planets are puffier than candy floss, yet wider than Jupiter. A few exoplanets are so swollen and airy that they seem almost impossible. They are enormous in size, sometimes wider than Jupiter, yet their mass is astonishingly low. If you could place one in a giant enough ocean, it might float. That sounds playful, but the physics behind it is serious and strange. These worlds are called superpuffs, and they seem wrapped in vast envelopes of hydrogen and helium that stretch far from their cores. Their gravity is so weak at the outer edge that the atmosphere balloons outward, giving them a ghost-like bulk. Kepler 51b is one of the best-known examples, a planet with the breadth of a gas giant and the density of spun sugar. These planets challenge formation models because they look fragile, inflated, and temporary. Some rocky worlds live so close to their stars that their day sides may glow like furnaces. If the planet is tidally locked, one hemisphere can face the star for ages while the other faces space. The result is not just a hot planet, but a world divided into permanent noon and permanent night, with winds and molten rock trying to carry heat across the boundary. They seem less like solid worlds and more like drifting celestial mirages, huge in silhouette, yet barely holding themselves together. A few scorching worlds may have permanent day and permanent night. Some planets orbit so close to their stars that gravity has slowed their rotation until the same face always points inward. One side lives under a fixed sun that never sets. The other remains in endless darkness with no dawn and no memory of noon. This is not a rare poetic idea. It may be common among close-orbiting exoplanets. The star-facing side can become hot enough to melt rock, while the far side may plunge into temperatures cold enough to freeze gases from the air. Between them lies a twilight zone, a narrow belt where conditions might be calmer, though still swept by violent winds trying to balance the world's extremes. On Earth, sunrise and sunset shape how we feel time. On these planets, time is different. A person standing still would not wait for day to end. They would have to travel to escape it. Some planets may have skies filled with vaporized rock. On the hottest rocky exoplanets, the atmosphere may not be built from water vapor, nitrogen, or carbon dioxide in the way we instinctively imagine. Instead, it could be made from stone itself. When a world orbits close enough to its star, surface rock can heat until it melts and begins to evaporate. That creates an atmosphere of mineral vapor filled with ingredients like sodium, silicon monoxide, and other gases released from molten ground. Picture a planet where the sky is not above a landscape, but rising from it, exhaled by the planet's own glowing crust. In some cases, this vapor may drift upward, cool, and then return as droplets or grains of condensed rock. It is an atmosphere born from the surface being slowly turned into air. That idea rewrites something basic in the mind. We tend to separate land from sky. On these worlds, the land itself may become the sky. One distant world may be losing its atmosphere like a comet. Some planets do not simply orbit their stars. They are being undone by them. There are worlds so intensely heated and blasted by radiation that gas streams away from them into space, forming long tails that resemble those of comets. One of the most striking cases is Gliese 436b, where observations suggest hydrogen is escaping in a huge cloud trailing behind the planet. It is a haunting image because a comet's tail feels natural to us, but a planet with one feels tragic and unstable. This is a world in the act of changing, perhaps shrinking over immense stretches of time as its star strips away layer after layer. The process is invisible to the eye, yet astronomers can detect it through the way the escaping gas absorbs starlight. A planet can be eroded by light itself. That makes every orbit feel less like a path and more like a slow surrender. There are planets where the wind may outrun the speed of sound. When astronomers talk about alien weather, they are not being casual. Some exoplanets may host winds so violent that they move faster than sound itself. These are not breezes or storms in any earthly sense. They are global rivers of gas driven by the enormous temperature contrast between the side facing the star and the side turned away. In that constant struggle to move heat around the planet, the atmosphere can accelerate to extraordinary speeds. On certain hot Jupiters, scientists think these winds may scream through the upper atmosphere at several kilometers per second. That is fast enough to circle continents in hours, fast enough to turn weather into something close to planetary violence. The effect is not just dramatic. It also changes what astronomers see, shifting hot regions away from the point directly under the star. So even from light years away, these invisible winds leave fingerprints. A planet can reveal its storms without anyone ever touching its sky. Some alien worlds may have clouds made from sand or glass. There are also planets that seem to be losing themselves. Under intense starlight, the upper atmospheres of some close-in worlds can heat and escape into space. A planet may trail a faint envelope of gas like a quiet comet, not because it is small and icy, but because its star is slowly sculpting the outer layers away. Clouds sound comforting until you remember that clouds are simply what the local environment allows to condense. On Earth, that usually means water. On a much hotter planet, the raw materials can be utterly different. Some exoplanets may form clouds from silicate particles, the same broad family of materials that helps make sand, rock, and glass. High in the atmosphere, where temperatures and pressure reach the right balance, those substances may condense into fine mineral grains and drift like alien weather systems. Imagine looking up and knowing the clouds above are not wet, soft, or cool, but composed of tiny specks of rock. On certain worlds, these clouds may glow, scatter starlight in unusual colors, or help control how heat moves through the atmosphere. They make the familiar shape of a cloud feel newly strange. A cloud is not defined by softness. It is defined by suspension. Even powdered stone can float when a world is strange enough. A few planets may have magma seas instead of oceans. Some rocky planets orbit so close to their stars that their surfaces may never fully solidify. Instead of continents, valleys, and seas of water, they may host vast pools of molten rock spread across the dayside like glowing inland oceans. These magma seas are not just a surface detail. They could shape the entire behavior of the world. Liquid rock can absorb heat, circulate, release gases, and interact with whatever thin atmosphere exists above it. That means the boundary between geology and weather begins to blur. On a world like K2141b, a person would not see waves breaking on the shore, but perhaps a horizon of moving fire. Some of these planets may even have rock vapor rising from the molten surface, then condensing elsewhere. The result is a planet that behaves less like a solid place and more like an active furnace. It is still a world, but one caught halfway between planet and eruption. Some worlds circle dead stars that should have destroyed them. When a star dies, it does not always do so peacefully. It swells, sheds its outer layers, and leaves behind a dense remnant such as a white dwarf or pulsar. That makes the discovery of planets around stellar corpses so astonishing. In many cases, those planets should have been consumed during the star's violent transformation. Yet, some are still there. They either survived impossible odds or formed later from the debris left behind. A planet that survives such an event has lived through the destruction of the very system that created it. A planet that forms afterward is stranger still because it means planetary birth can happen in the ashes of stellar death. These are not ordinary solar systems. They remind us that the story of a planet does not always begin in calm gas around a young star. Sometimes it continues after disaster in a place where almost everything familiar should have ended. One planet may have formed from the remains of a shattered star. There is at least one famous exoplanet candidate that sounds almost mythic, a dense world that may have formed from the wreckage of a destroyed star. The planet around Pulsar, PSRJ 1719-1438, is thought by some astronomers to be the carbon-rich remnant of a once larger companion star, stripped away until only its hardened core remained. If that interpretation is right, this is not merely a planet in the usual sense. It is a stellar remnant recast into planetary scale. It may be packed with crystalline carbon under such extreme pressure that the phrase "diamond world" entered public imagination. Whether or not that image is fully accurate, the deeper truth is astonishing enough. A world may exist that was not assembled gently from dust in the young disk, but carved out of the death of a star by gravity, radiation, and time. Planets can arise from birth, but also from ruin. Some planets may have no solid ground anywhere beneath their clouds. It is easy to picture landing on a planet, even a hostile one. Our imagination always searches for ground. But some planets deny that expectation completely. Gas giants and ice giants do not offer a true surface in the earthly sense. Rogue planets add another soft mystery. These worlds do not orbit a star in the ordinary sense. Some may have been thrown out of their systems by gravitational encounters, while others may have formed alone from small collapsing clouds. Without a nearby sun, they would be almost invisible, except for the rare moments when their gravity bends the light of something behind them. Their visible clouds are only the beginning of a deep descent into thicker and thicker layers of atmosphere, fluid, and compressed matter. Fall through the clouds of such a world, and you would not strike a solid plain or mountain range. Instead, pressure and temperature would rise without mercy. Hydrogen might shift into exotic states. Chemistry would grow stranger with depth. The idea of down would survive, but the idea of floor would not. This matters because many exoplanets we discover are giants of exactly this kind. They are worlds without shorelines, without stone underfoot, without a place to stand. A planet does not have to be solid to be real. Sometimes it is a deep atmosphere all the way into mystery. There are worlds where a year lasts only a handful of hours. Some exoplanets orbit so breathtakingly close to their stars that their whole year can pass in less time than a film or an afternoon nap. These are the speed demons of planetary astronomy. They complete full orbits in only a few hours, racing around their stars on paths so tight that our own solar system offers no real comparison. On such a world, the star would dominate everything. It would hang huge in the sky, pouring out heat and tidal force with relentless intensity. The planet's orbit would not feel stately or cosmic. It would feel desperate, as if the world were clinging to the edge of destruction. These ultra-short period planets are especially fascinating because many are small and rocky, which means entire solid worlds can survive in places where older models said they should not. A year becomes almost meaningless there. The basic rhythm that defines planetary life on Earth is compressed into something furious, intimate, and astonishingly fast. Some planets travel around stars that are far older than the Sun. Our Sun is middle-aged by stellar standards, yet some planets orbit stars that have been shining for far longer. That means there are worlds in the galaxy that may have existed while Earth was still assembling, or even before the Sun itself was born. One famous example is the planet around the star PSRB 1620-26, often nicknamed Methuselah, because the system may be 12 billion years old. To imagine a planet that ancient is to feel time expand in a new direction. This world may have seen the galaxy in a much earlier state, when heavy elements were rarer and the Milky Way itself was younger. Ancient planets matter because they test the timeline of planetary formation. They suggest that worlds began appearing very early in cosmic history. The universe may have been building planets for almost as long as it has had stars, making our own world feel young, late, and wonderfully recent. A few strange worlds may glow from their own leftover heat. Not every planet shines only by borrowed light. Some young, more massive worlds still carry enough leftover heat from their formation to glow in the infrared, radiating energy from deep inside themselves. This is one. A few exoplanets have been photographed directly because they are warm enough to stand out against the darkness when viewed with the right instruments. It is a beautiful idea. A planet can still be warm from the violence of becoming. Gas collapsing inward, material crashing together, gravity squeezing the interior. All of that can leave behind a reservoir of heat that lingers for millions of years. In some cases, that glow tells astronomers more than reflected starlight ever could, revealing clues about the planet's atmosphere, age, and mass. These worlds do not look bright to human eyes, but they are not cold silhouettes either. They are embers of creation, slowly cooling in the dark after their long and turbulent birth. Some planets may have hidden cores wrapped in vast mantles of ice. When we hear the word ice, we think of something brittle, pale, and cold enough to crack beneath a boot. Deep inside certain planets, ice may mean something far stranger. There are worlds that seem to sit between rocky planets and gas giants, with dense interiors that could include a central core wrapped in enormous layers of high-pressure ice. This is not ice you could skate on. Under immense pressure, water can lock into exotic crystal forms that do not exist naturally on Earth's surface. That means a planet may contain an internal architecture unlike anything familiar with rock at the center. Then, layers of compressed water ice, then lighter material above. The word habitable also needs gentleness. It does not mean comfortable, Earth-like, or alive. It usually means that, under the right assumptions, a world might allow liquid water somewhere on or near its surface. Atmosphere, chemistry, magnetic environment, stellar activity, and time all matter. A planet can sit in the so-called habitable zone and still be deeply unlike Earth. Some mini-Neptunes and ocean-rich planets may fall into this category. It changes how we picture a world from the inside out. A planet does not need a fiery mantle beneath its crust. Sometimes its hidden middle may be a kingdom of crushed, hot, and alien ice. There are giant worlds that skim so close their stars distort them. Gravity is not just a force that keeps planets in orbit. At very close range, it can become a sculptor. Some giant exoplanets travel so near their stars that they raise tides on the star itself, tugging at the stellar surface and helping distort the shape of both bodies. The effect is subtle from our distance, but the consequences can be dramatic. The planet may be stretched, heated, and tormented by tides, while the star can brighten or shift in response to the constant pull. In these systems, the boundary between star and planet feels less tidy than it does at home. They are locked in a close gravitational dance, each affecting the other in invisible ways. This is part of what makes hot Jupiters so extraordinary. They do not merely orbit, they interact. Their presence can change how their stars behave, proving that planets are not always passive companions. Sometimes a world is close enough to leave fingerprints on the sun it circles. Some planets may be tidally locked forever with one frozen face. Tidal locking does not always create a furnace on one side and a wasteland of darkness on the other. On planets farther from their stars, the locked night side could become a place of extraordinary cold, especially if the atmosphere is thin or absent. In that case, heat from the day side would not travel efficiently, and the hidden hemisphere might trap cold for ages. Gases could freeze onto the ground. Frost might build in permanent darkness. A locked world like this would have two personalities written directly into its geography, one facing warmth and one collecting winter without end. This possibility matters especially for planets around small red dwarf stars, where tidal locking is expected to be common. It means habitability is not simply a question of distance from the star. The rotation of the world matters too. A planet can sit in the right general zone for liquid water and still hide one face in the cold that never releases it. Others may keep one side blistering hot and the other dim. Some tidally locked planets do not divide into hot and cold in a simple, balanced way. The star-facing side can become unimaginably hot, while the far side remains not fully frozen, but dim, austere, and starved of energy. In between lies a world shaped by unevenness. The bright hemisphere may glow under relentless radiation with rock or cloud decks heated to extremes. The far side may not be a perfect ice ball if winds carry some warmth across. Yet it could still remain a place of deep shadow and muted skies. That contrast is part of what makes such planets so gripping. They are not only physically divided, they are divided in mood. One side is exposed and overwhelmed. The other is hidden and restrained. Even if no life could survive there, the geography itself feels dramatic. A planet can become a map of imbalance with climate, light, and atmosphere, all stretched between two radically different halves. Some alien skies may never know sunrise or sunset at all. On Earth, sunrise and sunset are among the deepest rhythms in life. They shape sleep, migration, weather, and the emotional texture of the day. Yet some exoplanets may never experience either. If a world is tidally locked, then from most locations the sky would be permanently fixed. Near the star-facing center, the sun would hang motionless overhead or slightly offset, never climbing and never falling. Even the familiar word planet becomes more flexible outside our neighborhood. Astronomers compare mass, radius, density, starlight, orbital period, and atmospheric clues, then build the best picture they can. Some worlds may be rocky super-Earths. Some may be mini Neptunes wrapped in thick gas. Some may be ocean worlds, lava worlds, or bare cores left behind after a larger planet was stripped. On the dark side, the stars might remain unchanged night after night because night would be all there is. Even in the twilight regions, the sun might sit forever near the horizon. This is more than a visual curiosity. It means time would be felt differently at the level of landscape. There would be no dawn chorus, no evening cooling, no long shadows arriving on schedule. A basic pulse we treat as universal would be missing. These worlds remind us that even something as ordinary as morning belongs to local physics. There are planets that orbit stars smaller and redder than ours. Most stars in the galaxy are not like the Sun. They are smaller, cooler, and redder, belonging to a class called red dwarfs. That matters because many of the planets we find, especially small rocky ones, orbit stars like these. A planet around a red dwarf may circle very close in and still receive only modest warmth because the star itself is faint compared with the Sun. From the surface, if there is one to stand on, daylight might look coppery or dimmer than what we know. The star could loom larger in the sky because the orbit is tight, yet the light would feel different, filtered through a redder spectrum. These systems have become central to the search for habitable worlds because they are common and easier for astronomers to study. In a way, the future of planet hunting has shifted towards stars that once seemed unremarkable. Strange planets may be most abundant around the galaxy's smallest suns. Some worlds circle stars so active, their skies may crackle constantly. A planet can be in the right place for liquid water and still be battered by the temperament of its star. This is a major concern around active red dwarfs, which can unleash fierce flares and bursts of charged particles far more often than the Sun. On a nearby planet, such activity might hammer the atmosphere, flood the sky with radiation, and trigger dazzling but dangerous auroras that never feel rare. If the world has a magnetic field, the heavens could light up again and again in restless curtains. If it does not, the star may slowly erode the atmosphere itself. That creates a powerful tension in modern astronomy. Some of the most promising planets for study orbit some of the most unruly stars. The result is a strange picture of possible habitability, one where a planet may sit in its star's temperate zone while living under a sky shaped by constant stellar anger, light, and electrical violence. Some planets may have been born far out, then migrated inward. A planet does not always stay where it forms. In many systems, giant worlds seem to have been born in the colder outer regions where ice and gas were easier to gather, then slowly drifted inward through the disk that surrounded their young star. That journey changes everything around them. As a giant planet moves, it can scatter smaller worlds, steal material, or trap neighbors into precise orbital patterns. In some cases, it may plunge so close to the star that it becomes a hot Jupiter, a giant world now roasting in a place where it could never have formed in the first place. This idea transformed planetary science because it turned solar systems into restless places rather than neat diagrams. They can reshape the destinies of everything around them. A planet's present address may hide a long and turbulent past, written not only in what it is, but in where it ended up. Some planets may have moons, though we still have not confirmed one. For all the thousands of planets found beyond our solar system, not one moon has yet been confirmed beyond real doubt. That is astonishing when you think about how common moons are here. Jupiter and Saturn are surrounded by them. Even tiny worlds can have companions. It would be stranger if exoplanets had no moons at all. So, astronomers keep searching for the faintest hints, tiny changes in timing, delicate shifts in light, slight wobbles that suggest a moon is circling a distant planet we can barely detect in the first place. The challenge is brutal because moons are smaller, dimmer, and easier to hide in the noise. Yet, the search matters enormously. A moon can shape tides, stabilize a planet's tilt, and transform the possibilities for climate and life. Somewhere out there, alien moons almost certainly exist. We may be living in the brief era before the first one steps from theory into certainty. There are worlds packed more tightly than entire solar system neighborhoods. Some planetary systems make our own feel spacious. Astronomers have found stars surrounded by multiple planets crowded into a region smaller than the orbit of Mercury. Picture several full worlds circling in the space we would normally assign to one. Their skies, if they had visible horizons, might be haunted by neighboring planets looming much larger than Venus ever appears from Earth. In systems like these, gravity writes a more intricate score. Each planet feels the pull of the others. Their orbits settle into delicate patterns that can remain stable for ages, provided every world keeps perfect time. It is one of the most thrilling lessons from exoplanet discovery. Solar systems do not need broad spacing to survive. Nature can build them compact, intricate, and beautiful, like a clockwork city circling a single sun. The result is not chaos, but a kind of compressed elegance where many worlds live astonishingly close together without immediately tearing one another apart. Some strange systems squeeze many planets closer than Mercury ever orbits. One of the clearest examples of planetary crowding is the TRAPPIST-1 system, where several Earth-sized worlds circle a tiny red star at distances that would all fit well inside Mercury's orbit. Yet, because the star is so faint, those close paths do not automatically turn the planets into furnaces. Instead, it creates a strange inversion of what we expect. A region that would be impossibly hot around our sun can hold a whole family of worlds around a dimmer star. The planets pass one another at close range and tug on each other in rhythmic patterns, locked into a chain of resonances that keeps their motion ordered. This gives the system an almost musical quality, as though each world is keeping time with the next. It is a reminder that the scale of a solar system depends on its star. A tiny sun can host a packed, intimate architecture that still leaves room for astonishing variety. A few planets may survive inside the swollen atmospheres of dying stars. When the sun-like star grows old, it swells into a red giant so enormous that nearby planets should be doomed. Yet some evidence suggests that certain worlds may briefly endure even as they plunge into the star's expanded outer layers. Survival in such a place would not mean calm orbiting beneath a peaceful sky. It would mean skimming through a vast stellar atmosphere, dragged by heat and friction, perhaps spiraling inward while disturbing the star from within. In some cases, a planet may be consumed. In others, it may help strip away stellar material or leave clues in the star's spin and brightness that betray its final struggle. This idea is gripping because it turns the death of a solar system into a contact event. A planet does not merely watch its star transform from afar. It can enter the star's outer body and interact with it directly. The last chapter of a world may unfold inside a sun. Some alien worlds may have seasons driven by wildly tilted orbits. On Earth, the seasons are shaped by the tilt of our axis, which gives us a reliable cycle of changing sunlight. But some planets may experience far more dramatic seasonal patterns if their axes are tipped at extreme angles. Imagine a world leaning so far over that one pole points almost straight at the star for part of the year, while the other sinks into long darkness. Such a planet would not have familiar spring, summer, autumn, and winter. It might swing between months of relentless heating and months of deep freeze with strange transition periods in between. The star's path across the sky would feel unnatural, perhaps circling the horizon or vanishing for ages. Climate on such a world could be difficult to predict, especially if oceans, clouds, or thick air redistributed heat in unusual ways. It reminds us that a season is not a universal experience. It is a local consequence of how a world chooses to lean. There are planets whose paths are so stretched, their climates swing brutally. Not every planet travels on a near circular path like Earth. Some follow highly elongated orbits that carry them close to their stars, then fling them far away again. That means a single year can include enormous swings in temperature and energy. A world might spend part of its orbit in comparative chill, then rush inward and experience a surge of heating so extreme that its atmosphere expands, chemistry shifts, and any stable weather pattern is thrown into gross confusion. This is not simply a longer winter and summer. It is a planet moving between two very different physical states as it loops around its star. The changing distance affects light, heat, and even winds in ways that would make Earth feel almost impossibly calm by comparison. Such worlds are thrilling because they show that a year can be a drama, not a cycle. Orbit itself can become the engine of planetary violence, rewriting the climate again and again. Some giant worlds may be heated more by tides than starlight. A planet does not need to hug its star to become hot. In some cases, gravity from a star, a nearby planet, or a moon can flex a world so relentlessly that the interior heats from within. This is called tidal heating, and in extreme cases, it may rival or exceed the warmth a planet gets from starlight. We see a modest version of it in Jupiter's moon Io, but exoplanets could take the idea much further. If a giant world follows an eccentric orbit, its shape may be stretched and relaxed over and over again, kneading the interior with every pass. That friction can generate immense heat, drive internal motion, and possibly transform the atmosphere and surface. It is a thrilling reversal of instinct. A planet can glow with energy not because the star is close, but because gravity is constantly working it like a living machine. A world can be cooked by motion itself. A few planets may glow red from constant volcanic resurfacing. There may be worlds where volcanoes are not occasional disasters, but a permanent part of the landscape. On such planets, tidal heating, youth, or internal chemistry could keep magma rising so often that the surface is continually renewed. Fresh lava would darken, crack, and cool, only to be broken open again by newer flows. From a distance, parts of the planet might glow with a dull red heat, especially on the side facing away from direct starlight. This is more than a dramatic image. Constant resurfacing changes the whole character of a world. It can refill the atmosphere with gases, erase impact craters, and keep the crust from growing old. A planet like that would not feel settled. It would feel restless and unfinished, as if geology had been turned up too high. We are used to imagining planets as ancient and stable. Some may instead be places where the ground itself is always in the process of becoming new. Some rocky worlds may have crusts made from minerals rare on Earth. Earth's crust feels ordinary only because it is home. In truth, the minerals that dominate our planet reflect a very specific history of temperature, chemistry, water, and plate activity. Change those ingredients, and an entirely different kind of rocky world may emerge. Some exoplanets could have crusts rich in minerals that are rare at Earth's surface, shaped by hotter conditions, unusual elemental ratios, or the absence of water-based weathering. On a carbon-rich world, for example, the upper layers might include forms of carbon-bearing rock far more abundant than anything common here. On an ultra-hot rocky planet, the surface could be built from minerals stable only under brutal heat, with familiar Earth rocks unable to survive for long. This matters because the crust is not just scenery. It controls how a planet reflects light, releases gases, stores heat, and changes over time. Even stone itself may tell very different stories on strange planets. There are planets where noon may be hot enough to melt stone. On some rocky exoplanets, the star beats down with such force that midday temperatures may rise high enough to melt the ground itself. This is not the warmth of a desert or the heat of a volcano. It is a planetary noon, so intense that rock can soften, glow, and perhaps even flow across the surface in molten patches. On worlds orbiting red dwarfs at very close range, or on ultra-short period planets, whipping around their stars in only hours, the day side can become a place where ordinary geology stops behaving in ordinary ways. The boundary between surface and atmosphere may begin to blur. What makes this so striking is how it changes the meaning of daylight. We think of noon as the bright center of the day. On these planets, it becomes a destructive force. Sunshine is no longer life-giving or pleasant. It is a furnace descending from the sky. Some strange worlds may have nights brightened by rivers of lava. Darkness on another world does not always mean blackness. On a planet with active volcanism or molten regions, the night side may be lit by lava flows, glowing cracks, or heat radiating from recently erupted rock. Imagine standing beneath a sky of stars while the land around you shines red in branching lines, as though the planet were lit from below by its own wound. This is one of the most haunting possibilities in exoplanet science because it gives night a different source of light. The brightness belongs to the world itself. On a tidally locked planet with a searing day side, some of that heat may even be carried toward the darker hemisphere, feeding volcanic regions or magma movement beyond the line of eternal sunset. A world like this would feel alive in an unsettling way, glowing not with reflected light, but with exposed fire from within. A few planets may hide deep oceans beneath global shelves of ice. Some distant worlds may look frozen and lifeless from the outside while hiding something extraordinary below. If a planet or large moon has enough internal heat, perhaps from radioactivity or tidal flexing, a thick shell of surface ice could cover a deep liquid ocean beneath. That means an apparently silent white world might contain a vast dark sea sealed away from space for ages. The ice above would not be a mere crust, but a roof over an alien ocean, protecting it from radiation and preserving heat below. In our own solar system, moons like Europa and Enceladus make this idea feel real and urgent. Beyond the solar system, similar worlds may be common. The fascination here is profound. A planet can conceal its most interesting feature under miles of ice. A frozen face does not always mean a frozen heart. Sometimes the most promising ocean on a world is the one no telescope can directly see. Some ocean worlds may never have a single continent anywhere. Earth's oceans are vast, yet they are broken by continents that shape climate, currents, and the history of life. Some exoplanets may never have any land at all. Their surfaces could be one continuous global sea, uninterrupted by coasts, mountain ranges, or river-carved boundaries. From space, such a planet might look almost serene. A round blue world with clouds drifting above an unbroken ocean. But the absence of continents would change everything. Weather patterns might be more uniform in some ways and more extreme in others. Nutrient cycles would be different. There would be no beaches, no soil, no rocky shore where land and sea meet. Even the chemistry of the atmosphere could follow a different path over time. What grips the imagination here is how thoroughly this alters the meaning of a planet. We often think of land as normal. Yet a world can exist with no dry place at all, only water from horizon to horizon. There are planets that may be richer in carbon than Earth. Earth is not the only recipe for a rocky world. If a planet forms in a region where carbon is especially abundant compared with oxygen, the resulting world may be built from a very different chemical foundation. Instead of the silicate-heavy geology that dominates Earth, such a planet might contain far more carbon-based materials woven through its crust and mantle. This could change everything, from the minerals at the surface to the way heat moves through the interior. A carbon-rich planet would not necessarily be a glittering fantasy of diamonds everywhere. It might be dark, dense, and geologically unfamiliar, filled with substances that are unusual here, but natural there. The thrill of these possible worlds lies in what they reveal about planetary diversity. A rocky planet does not have to mean Earth-like. Nature can take the same broad idea, a solid world under gravity, and build it from an entirely different chemical imagination. Some carbon-rich worlds may form layers of graphite or diamond. Under the right conditions, a carbon-rich planet may do something almost unbelievable. Deep inside, immense pressure could squeeze carbon into crystal structures such as diamond, while shallower layers might contain graphite or other carbon-heavy materials. This does not mean a sparkling jewel world waiting to be mined. It means a planet whose interior geology could be shaped by the same element that forms both soot and gemstones on Earth, but on a scale that defies ordinary thought. The deeper one goes, the more pressure transforms simple chemistry into something harder and stranger. That possibility matters because it shows how planetary interiors depend on composition as much as size. A world made from a different elemental starting point may not just look different on the surface. It may be fundamentally different all the way down. Beneath an alien crust, entire layers of carbon could be stacked like an unfamiliar geological poem written under crushing force and time. A few strange planets may have atmospheres stripped by fierce stellar wind. A star does more than shine. It also blows a stream of charged particles outward, and on some planets, that wind may be fierce enough to erode the atmosphere itself. Worlds orbiting close to active stars are especially vulnerable. Over long spans of time, the upper air can be heated, ionized, and gradually carried off into space. This process can transform a planet's fate. A world that once had a thick envelope of gas may be left bare, dry, and far more exposed than before. The violence is slow on a human timescale, but it is relentless. It turns habitability into a race between atmospheric replenishment and stellar attack. For astronomers, these stripped atmospheres are not just losses. By watching gas escape, scientists can infer the strength of stellar winds and the fragility of planetary air. A planet's sky is not always stable. Sometimes it is something the star is actively trying to steal. Some small worlds may be little more than exposed planetary cores. Among the strangest exoplanets are small, dense worlds that may once have been much larger. Astronomers think some of them began as sub-Neptunes or gas-rich planets wrapped in thick atmospheres. Then, over time, intense radiation and stellar wind blasted those outer layers away, leaving behind the hard central remnant. What remains may be an exposed planetary core, the stripped heart of a world that lost almost everything around it. This is fascinating because it turns planets into archaeological objects. A dense rocky may not be a planet that was born small. It may be the survivor of a long process of planetary erosion. In a sense, we are looking at the skeleton rather than the body. These worlds show that planets are not fixed categories. A gas-rich world can become something leaner, harsher, and more compact. Sometimes the most revealing part of a planet is the part left behind after its outer self is gone. There are planets that seem to have lost almost everything but their center. Some exoplanets feel less like complete worlds than more like remnants. They are extremely dense, very close to their stars, and so stripped down that astronomers suspect they may be the surviving centers of much larger planets. Imagine a world once wrapped in deep gas or volatile-rich layers, orbiting too near a star that gradually cooked and blew those outer regions into space. What remains could be the core, compressed, battered, and left exposed after billions of years of loss. This idea is powerful because it gives planets a biography of attrition. We are not only seeing how a world forms, but how it can be peeled back until the innermost part is all that is left. It also changes how we look at small rocky planets near hot stars. Some may not be pristine little Earths. They may be the leftover hearts of giant worlds surviving after nearly everything else was erased. Some giant planets may orbit sideways over their star's poles. We tend to imagine planets circling above the star's equator because that is how our solar system is arranged. Yet, some giant exoplanets break that rule spectacularly. Their orbits are steeply tilted, and a few may pass almost over the star's poles, moving in paths that would look sideways compared with the neat flat layout we know. This is one of the clearest signs that solar systems can experience major upheaval. Such orbits may be the result of violent interactions with other planets or nearby stars, events that knocked a giant world out of its original plane and left it circling at an astonishing angle. The result feels deeply strange because it turns a solar system from a calm disk into a three-dimensional puzzle. A planet can rise over a star's pole rather than slide around its waist. Even orbital direction, something that once seemed fundamental, turns out to be another place where nature likes to improvise. A few strange worlds move on paths badly misaligned with their stars. Our solar system taught us to expect order. The planets circle in nearly the same flat plane like marbles rolling around a well-made track. But some exoplanets ignore that pattern completely. Their orbits are badly tilted compared with the spin of their stars, as if the whole system was knocked sideways long after it formed. This is one of the clearest signs that planetary systems can suffer violent pasts. A giant world may have been shoved by another planet, tugged by a distant star, or dragged into a new angle through a long gravitational struggle. The result is a path that cuts across the star's equator at a bizarre slant. From afar, that may seem like a subtle detail. It tells us that some worlds are not living in calm architecture. They are survivors of upheaval, still carrying the crooked signature of old cosmic collisions in the shape of their years. Some planets may have been flung into lonely space by gravitational chaos. A planetary system can look stable for millions of years, then suddenly turn brutal. When several giant worlds form together, their gravity can begin a slow contest of nudges and near misses. One orbit shifts, then another. A close encounter happens, and in that moment, a planet may be hurled outward with such force that it escapes the star entirely. What was once a member of a solar family becomes a castaway. This kind of ejection may be one of the main ways rogue planets are made. It turns planetary history into something dramatic and precarious. A world can begin in a bright young system full of heat, dust, and neighboring planets, then end up drifting through interstellar darkness because gravity became unstable for just long enough. That possibility makes every quiet orbit feel less guaranteed. A planet is not always born to stay. Sometimes it is born into a family that eventually throws it away. There are rogue worlds warmed only by radioactivity and trapped heat. A planet without a star sounds like a frozen corpse. Yet some rogue worlds may keep a faint inner warmth for billions of years, even while drifting through the dark between stars. The source would not be sunlight, but the slow decay of radioactive elements in the interior, combined with the leftover heat from the planet's own formation. Deep below the surface, that heat could linger like an ember sealed inside stone. If the planet were large enough and wrapped in insulating layers of rock or ice, the temperature underground might remain surprisingly stable. What grips the imagination is how little a world may need to avoid becoming completely dead. No dawn, no seasons, no star overhead. And still, somewhere beneath miles of darkness, heat might endure. It is a powerful correction to our instincts. A planet does not need to live beside a sun to keep a hidden source of energy. Sometimes the fire is carried within. Some free-floating planets may still carry thick blankets of atmosphere. When a planet is flung into interstellar space, it does not automatically lose everything that made it a world. Some may keep dense atmospheres long after leaving the star that once warmed them. That matters because a thick atmosphere can act like a blanket, trapping internal heat and slowing the loss of warmth into space. Hydrogen is especially good at this, and on a large enough rogue planet, it could help create a surprisingly insulated environment. From the outside, such a world would look cold and dark, but the atmosphere could be doing quiet work, holding on to what little energy remains. This idea changes the emotional texture of a rogue planet. It is no longer just a lonely rock in the void. It may be a sealed world wrapped in its own sky, carrying a remnant of habitability into the black. A planet cast out by gravity may still remain self-contained, secretive, and strangely alive with retained warmth. A few lonely planets may even keep dark, hidden liquid water. The phrase liquid water usually brings sunlight to mind. Beaches, rivers, or at least a warm star in the sky. But a rogue planet may not need any of that if the conditions are right. Beneath a thick atmosphere or under a crust of insulating ice, internal heat could be enough to keep water in liquid form far below the surface. That means one of the most important ingredients for life might exist on a world where no sunrise has happened for billions of years. The water would not glitter. It would not lie beneath clouds lit by a sun. It would remain in darkness, hidden and sealed away. That possibility is astonishing because it widens the map of where life-friendly conditions might exist. Habitability becomes less about location and more about structure. A planet can leave its star behind and still protect an inner sea. The galaxy may contain warm, wet worlds drifting through absolute night. Some strange worlds may be born in disks twisted by companion stars. Planetary systems do not always form around a single star shining alone. Many stars are born with companions, and those companions can twist the surrounding disk of gas and dust into strange shapes before any planet has fully emerged. Instead of a flat, orderly pancake, the material may become warped, tilted, or even broken into separate rings that do not line up. Planets forming in such an environment would grow inside a birthplace already bent out of shape. Their orbits could end up unusual from the very beginning, not because of later chaos, but because the nursery itself was distorted. This matters because it gives us another route to planetary weirdness. A strange orbit does not always mean a violent past. Sometimes it means a strange childhood. The presence of another star can reshape the cradle before the worlds inside it are even finished. Nature may be building odd planets from crooked blueprints right from the start. There are planets in systems where two suns chase each other endlessly. In a binary star system, the two suns do not sit still while a planet calmly circles them. They chase each other, each pulled by the other's gravity, moving around a shared center in a ceaseless loop. A planet in such a system must live with two moving sources of light, each shifting position as the days and years pass. The sky would never feel simple. Sometimes the stars might appear close together. At other times, they would separate. One might set while the other still burns above the horizon. The beauty of this arrangement is matched by its difficulty. Planetary orbits in such systems must find a stable rhythm among constantly changing gravitational forces. That is what makes them so captivating. They prove that even a sky ruled by two suns in motion can still host a lasting world. A system that seems too complicated for stability can become a home for planets after all. Some double-sun worlds may see shadows crossing in complicated rhythms. On Earth, shadow is simple. One sun means one dominant direction of light. On a planet orbiting two stars, light becomes more theatrical. If the suns are separated enough in the sky, objects could cast two shadows at once, each pointing a little differently, each changing as the stars move. One shadow may sharpen while the other fades. At certain moments they could overlap. At others, they might stretch apart across the ground like crossed fingers. Even a simple day would feel more layered. Morning and evening would not arrive in one clean sweep because the stars might rise and set at different times. Imagine landscapes where the light never settles into a single mood because the sky itself is working in pairs. This is not merely pretty. It reveals how profoundly a star system shapes the experience of a world. A second sun does not just add brightness. It adds complexity to every hour, every outline, and every moving shape. A few planets orbit stars that pulse, flare, or fade dramatically. Not every star is steady. Some brighten and dim in regular cycles. Some erupt with sudden flares. Others pulse as their outer layers swell and shrink. A planet circling such a star would live under a sky where the source of light itself behaves unpredictably or rhythmically in ways that would reshape weather, temperature, and atmosphere. Imagine a world where daylight strengthens and weakens, not because of clouds or seasons, but because the star itself is changing. In a flare-rich system, the sky may suddenly flood with radiation. In a pulsating one, the planet could experience recurring shifts in energy as though the sun were breathing. These stars remind us that planets do not orbit passive lamps. They orbit active bodies with personalities of their own. A strange planet may be made stranger still by the star it depends on. Sometimes the weirdest thing in the system is not the world, but the sun above it. Some worlds circle pulsars, the spinning corpses of exploded stars. A pulsar is what remains after a massive star explodes, and its core collapses into an object so dense and fast spinning that it sweeps beams of radiation through space like a cosmic lighthouse. And as the journey grows quiet, the strangeness begins to feel less like a collection of oddities and more like a message from the universe itself. Planets are not made from one simple recipe. They are shaped by heat, gravity, migration, impacts, atmospheres, chemistry, starlight, and time. Our own Earth is still precious in that larger story, not because every other world is less interesting, but because every other world helps us see more clearly how delicate and specific this blue planet is. Somewhere in the dark, a planet may be raining minerals into a permanent night. Somewhere else, a giant world may be crossing the face of its star every few days. Farther out, a lonely planet may be carrying its small store of heat through interstellar space, unseen except by gravity. And all of them, strange and quiet, remind us that the universe has more ways to make a world than the mind can hold at once.